Good evening, everybody. Welcome to Slooh. You are tuning in to my Intro to Astronomy course, and tonight we are going to be talking about gravitational lensing and what this means when we look up into space and we see different objects. What are we seeing objects that are actually presented to us the way that they exist in space? Are they distorted in any way by the light that is in front of them, such as we know that clouds of gas and dust distort light? So I'm just checking for a second that I have my audio. Bear with me. My computer is actually on the fritz. I'm afraid it's nearing the end of its life, and I am using my husband's computer right now. So let me just check that the audio is working correctly. Okay, my audio is working. Thanks for bearing with me. Okay, so if you're following along with me at slooh.com, I am screen sharing and you will be able to see what I'm looking at. Sometimes I have some diagrams and some images that help to tell the story with me. So please join me over there and I will switch that on right now. So you're watching my streaming. There we go. Okay, so right now I'm just starting out on our website. Like I said, where you should be following me would be under Livecast in the Space Situation Room. This is our Chile One Telescope that's online tonight. And if you've been following along the past few days, actually it's been probably almost a week now, the Canary Solar Scopes, well, the Solar Scope and the rest of the scopes are online, and it's amazing, and they were actually online a little bit earlier tonight, which was really awesome. So, but tonight we are graced with the Chile One Telescope, and we will be watching what we're looking at there. And so when you look at this image, particularly there's probably not any sort of gravitational lensing that we can pick out, but think about how it could exist and how we could be looking at things that have been gravitationally lensed by objects that are in front of them. So when we talk about gravitational lensing, the two words in that phrase, gravitation and lensing, are the big components here, and we're going to break them down into two. And so first we're going to talk about lens. A lens, when you think about a lens, you might think of a magnifying glass that you use to read the newspaper, or a microscope, or a telescope, which, as we all astronomers like to think about, we're thinking about telescopes, right? So when we think about a lens, it can either focus light for us, or it can make light larger and more unfocused, depending on what kind of lens we're looking at. So, but basically you're thinking about a curved piece of glass that would magnify objects, like a telescope. So when glass gets in the way of light rays are bent. And so we have a light ray coming in, and it gets bent through the glass and then comes out the other side. So if we have a convex lens, the light is going to come through the lens, and then it's going to be focused coming through the other side. The light rays are bent, and when they come through the other side, they're focused on what we call a focal point. So a telescope has this sort of lens that is pulling the light in and focusing it, and then it also has a second lens, which is called the eyepiece, which then takes the converged image and separates it into a image that is ready for your eyes, which your eyes are also a type of lens. So this is the kind of lens that we look at when we, if you were to build your own telescope and see what the lenses on the inside look like. But in space, massive objects actually bend light like a lens. So massive objects have so much gravity that they warp the space-time fabric, like we talked about last week when we were talking about gravitational waves. So let's look at a couple images of what this means. So if we think about space-time, we think about a 4-dimensional fabric. We have 3 dimensions of space, x, y, and z, and then we also have a dimension of time. And when we combine those, because we do believe that they are intricately linked, we have a 4-dimensional universe, and it's called the space-time fabric. And so if you picture like the image we're looking at here, you can kind of see it's like a grid or like a bed sheet. If you and your friend were holding a bed sheet at the 4 corners all stretched out, this is the analogy I used last week, and you put a bowling ball in the middle, that bowling ball is going to warp the fabric of the bed sheet, and it's going to yank it in a direction. I don't want to say down because, you know, space doesn't have any sort of up, down, left, right direction necessarily. That's a man-made construct, human-made construct, sorry. But so if we have a bowling ball on it, it's going to warp this space-time an awful lot. If we have just a little marble on it, it's going to warp the space-time considerably less. So the more massive the object, the more warping that occurs. So an interesting graphic that I found that I really liked how this demonstrated was on Quora. So if we have the sun and the earth, we can see how massive the sun is and how much space-time it's warping here. If there's an object behind the sun, a star, this is where the star actually is, its light is going to come around, it's going to be warped by the space-time fabric because the space-time fabric is warped, so the light is going to follow the direct path that it is traveling along space-time. And it's going to reach Earth, and when it reaches Earth, it looks to us, because we just assume that the star is straight out from where we see it, that it's over here. And so this is kind of a whole nother lecture. It's really interesting about like the motion of nearby objects in our sky and the difference between like proper motion and parallax. It's really interesting, but maybe I'll add that to the end of this course. I didn't think about putting that in here. Anyway, so, but it's interesting to note how the light is distorted when it has to come around an object that is supermassive like the sun. But okay, so what am I talking about? We have all this mass, it's distorting the space-time fabric, and so the light, instead of being able to travel along a straight line like it wanted to, it has to go around the object. So if there's a galaxy hiding in the distance behind a star, the star is going to warp the space-time around it due to its mass, which bends the galaxy's light that's trying to get through around itself like a giant lens, and the light becomes magnified. And it looks like a distorted ring of light around the star. Kind of like in this graphic. So if we have, this is a different example. So anything can do this. It was just an example galaxy star. We have here a galaxy and a galaxy cluster. So anything with a lot of mass is going to be distorting space-time like this. And so we look at this galaxy cluster that's in the way of this beautiful galaxy behind it that we want to see. Earth is here. This is a straight line. So Earth is here, we're trying to see through the galaxy cluster. We can't, but the galaxy behind it, the light that's traveling from it is actually distorted around the galaxy cluster and refocused in on us. And so this distortion, this lensed galaxy image, is going to appear to us like a ring. So this is called the Einstein ring because, of course, Einstein in all of his fame and glory theorized this. And so this is an example of an Einstein ring where if the object that is in the most distance is lensed so perfectly around the object in front of it, it will create a perfect ring around it. And so when we see a ring that's really, really close to being perfect like this, it's really beautiful. And it's called an Einstein ring. So we have in this image, it's a luminous red galaxy that has gravitationally distorted the light from a much more distant blue galaxy. So you can note the real colors in here. The galaxy in the front is red, and it's distorting what would be a blue galaxy behind it. So gravitational lensing allows us to see distant objects that would normally be blocked from our view by something large in the way. And it makes it sound like, you know, we're kind of making this happen, but it's actually really just a nice coincidence that this happens for us. So another example, another famous example that I had shared on the livecast slate advertising the show tonight is the smiley or Cheshire cat image. It's a galaxy cluster and gravitational lensing Einstein ring discovered by a team of scientists with the Hubble Space Telescope. So we have a bunch of galaxies here, and then we have a galaxy behind it that's creating this Einstein ring. And so it makes the little smiley face. And if you watch Alice in Wonderland, it looks like the Cheshire cat. And another fun one is the double Einstein ring. So I'm not talking about the theory with black holes that can distort this sort of lensing so much that it creates multiple rings. But what I am talking about is if you have multiple objects in the distance being distorted by the closer object. So if I have a star in front of me, and then behind it I have a galaxy, and then behind that I have another galaxy, if the distances are all appropriate and far enough apart, both of those galaxies are going to be lensed by the close-up star. And you're going to get a double Einstein ring. You're going to see two different rings for the two different objects that were behind the initial object. So aside from the pretty pictures that gravitational lensing makes for us, does it have any other use? It allows us to see objects that we normally wouldn't have been able to see because they would have been blocked. But let's talk about it also as a tool for communication. We know that the greatest speed that any sort of communication signal can travel is the speed of light. It is a finite speed. It's about 300 million meters per second. And aside from light, we actually haven't achieved reaching any such speeds yet with anything. So it's just light that can travel at this finite speed, but it is incredibly fast. But of course, space is doubly incredibly big. And so traveling at the speed of light is great, but it doesn't really get us very far, very fast. So as a spacecraft gets further away, it also becomes harder for us to detect its signal. Its signal becomes weaker, so we need bigger and bigger detectors, right? Of course, it's easier for us to see the planets in our own solar system than it is for us to see exoplanets around a star further away or, super, super distant galaxies versus ones that are up close. So we would need a detector that is much bigger, almost like the size of a small city, if we ever got to the point that we sent a probe to another star and wanted to send a signal back to us. We would need a super large detector to receive that signal. But science says that we can use the sun as a giant gravitational lens to strengthen that signal. I mean, why can't the sun? So gravitational lenses, they don't discriminate on what type of light they bend. They bend all type of light, all kinds of electromagnetic radiation. So in this case of looking at these Einstein rings, it's bending visible light, but it also bends infrared light and gamma rays and radio signals and other sorts of communication signals that we might want to use that aren't direct visible light. So if a spacecraft was around another star, we could talk here about aliens, or we could talk here about our future space travels, and maybe we have a probe around another star. We want to send a message back to us, or the aliens are trying to message us, and they send the message in the direction of our sun. The sun's gravitational lens would magnify and boost the signal so that we could pick it up. The sun acts as a gravitational wave. It has a lot of mass. It distorts space-time. I'll go back to this diagram here. And it's going to warp the light from the signal behind it around it and focus it back onto our Earth for us. The main problem with this is that we would need a really, really large receiving dish, but it couldn't be on Earth. If you think about really large radio telescope arrays and such, like the VLA, which actually just stands for Very Large Array. Some of our acronyms are pretty funny. But really large receiving dishes on Earth wouldn't even be able to receive a signal like this that was gravitationally warped around the sun like that. We would need to send it out into space. So like other lenses, our sun, when it acts as a lens, creates a focal point. I mentioned this earlier, but let's go back to talking about it. When we have a convex lens, so this is like a little optics class here, the light comes through the lens, and as it's bent, it's focused into what we call the focal point before it starts to spread back out again, and this is where we would have the eyepiece if we wanted an eyepiece like a telescope. But this focal point isn't just arbitrary. It is mathematically determined based on the size of the lens. So the smaller the lens, the closer in the focal point. So the sun has a really distant focal point. This is the place where all of the waves, the radiation waves come together. And the sun actually has multiple focal points, which we call a focal line. So if you imagine that depending on the signal that you're sending around the sun and the distance away that the signal is behind the sun, the focal point would be maybe here or here or here or here in a line. It would be along this plane, but depending on the size of the signal behind the sun and how far away it is from the sun or the lens here, remember the sun is our lens, this is where the focal point would be determined. So we have this focal line, but the closest point on that focal line for us is actually over 80 billion kilometers away, more than 550 times the distance from the Earth to the sun. So more than 550 AU. It's really far away. To get a receiver to that distance would take about 160 years. The furthest we've ever sent something from Earth is Voyager 1, which is at about 20 billion kilometers away, and that took 40 years. So 4 times that distance to get to 80 billion kilometers is 4 times 40 years, which is 160 years. So it would take a really long time to get this receiver out to that place. Now, that doesn't mean we shouldn't do it, but that just means that my grandkids' kids will enjoy this. So also, though, that is the closest point on this focal line, but the further we go along the focal line, the better our receiver would be. It would be easier to avoid solar flares and other interference from the sun that would potentially ruin our communication signals. So the further we could get, the better. The next issue is that the signal would be all sorts of distorted because of the sun's gravity and warping of space-time. You know, this Einstein ring, when we look at this, let's see here. Now, certainly, that is not what the galaxy actually looks like behind that red galaxy. The blue galaxy behind the red galaxy, of course, doesn't look like a circle like that. Look at how all distorted its light is. So now we need to kind of piece it back together. So we need to reconstruct this deconstructed signal. And of course, this assumes that we are getting messages from sources on the exact opposite side of the sun. When we look at this, you know, you're looking at the computer screen, you're seeing this red galaxy, and right behind it, not directly, like at a super far away distance from behind it, but along the same line of sight is the blue galaxy. So when we use the sun as a gravitational lens, the focal point, we are assuming that it would be directly on the other side of the sun from where our receiver is. Now we can go in different directions around the sun to kind of choose, you know, where we want our receiver to be, but wherever we choose our receiver to be, the source needs to be directly on the other side. And if we wanted to send a message using the sun as a lens to magnify our message, we would have to assume that the receiver, whether it be our own sort of probe that we had sent out into interstellar space to study stars, or whether it be an alien that we're trying to talk to. Keep bringing up aliens. It entertains me. I read too much sci-fi. We are assuming that this receiver is also on the other side of the sun as well, from where we're sending the signal, presumably from Earth. But we could use the sun as a big telescope lens. So if we, you know, this whole communications concept is entertaining. It's definitely possible, but it's in the far, far future. So in the meantime, we can use the sun as a big telescope lens. So instead of translating messages and getting the probes in the right spots, we could just use the lens to get a close-up view at whatever's directly behind the sun, like exoplanets or distant galaxies. It's like having a telescope with a lens more than 1 million kilometers across. Really, really big telescope. We would not consider this a backyard telescope. Although, however, the sun is kind of in our backyard, right? So, I mean, it could be our backyard telescope, but this would be a backyard telescope that would be shared by all of us humans on Earth. A nice global mission. So that was kind of like a little bit of a quickie show tonight, but you know, it's a topic that there is a lot of research on because it shows us things that we wouldn't otherwise be seeing because they're blocked by the light in front of them. But in terms of using it for future communication and as its own sort of telescope lens for our personal use, it's definitely a new field of research in that sense. So don't think that we'll be receiving any communications via the sun's gravitational lens anytime soon, but it does make for some really awesome images when we use distant stars and galaxy clusters as gravitational lenses to see objects that are behind them. So I'll leave you off tonight back with the Chile One Telescope, which is online. If you haven't noticed, you can click back and forth between wide field and ultra wide field. That's a nice new feature. Next week, I'm actually going to have the show on Tuesday night. We have a conference, so the NSF conference is coming up in a week and a half, and we're really excited about that. That's the conference for our grant, but right before that, I'm actually going to be in Georgia for the National Science Teachers Association conference. So that's going to be really fun, and I'm excited, but I will be flying on Wednesday, so I'm going to have to bump the show up to Tuesday night. So it will be a night earlier, but it'll be same time at 7:30, and you'll be able to watch it later in our past live casts if, you know, Wednesday is your preferred night. Next week, we're going to talk about string theory and higher dimensional space and all of those unproven, weird, but really cool and not disproven theories. I love talking about that kind of stuff. So we'll enjoy some of that next week. In the meantime, I hope you have clear skies. I hope you're enjoying our telescopes finally being online. And cheers. Good night, everybody.